My name is Ivan. I'm going to give a pretty high-level last talk, so I don't want to bother everybody with like very heavy technical stuff. So I'm going to be more like high-level philosophical, but also show how our model works, show some example what the model can do, and talk about our company first, like who we are and where we're coming from. And I would like to ask you questions. How can we build AI that understands physical world? What does it even mean for the AI to understand the physical world? Now, a little bit about the company. I'm from Archetype AI. It's a 5 co-founders. Company is pretty young. We've been operational for about 1 year. We got funded at the end of 2023 and been operational for 1 year, so 1 year running the company. And we're all coming back from Google, and we're coming from very different perspective on the physical world and interaction with the physical world. We're coming from sensor world. So when we were at Google, we built a lot of work where we use very complex sensors. Like, for example, one sensor we invented was a SOLI, which is a picker radar, which was then shipped in phones, in multiple physical devices. It's a very complex signal. And the problem is, how can you understand physical world from extremely complex and ununderstandable, unintelligible signal like a radar? So it's all done through deep learning, and we now ship a bunch of stuff for like human motion, so forth, right? So we left Google and started a company. And I think Archetype AI was actually the first startup, the first company who really bet on physical AI. So we said, like, we're going to be a physical AI company. Before, like us, really not many people talk about physical AI. And I have a proof for that, because the handler for the Twitter is a physical AI. So that was available. Everybody could get it, so we got it. And instead of using our company's handler, we said we're going to be a physical AI company. That's what we are. So, and what we're working is building a foundational model which can understand physical world through sensor data. We're mostly focusing on understanding and less on robotics. So recently, because of Jason Huang, I think his talk at CES, he really popularized this term, physical AI. And he said, like, this is a hockey stick. Physical is going to be the next revolutions. I'm really thankful to him. It's really helped us, because when people search for physical AI, everybody comes to our Twitter account. So our number of people on Twitter growth, thanks to him. So, but I think what's the difference is that, like, right now, kind of the whole conversation about physical AI is skewed toward robotics. And everybody talks about, oh, physical AI is for robots or self-driving cars, and very much about camera data. It's like all cameras, and just look from the cameras and so forth. So we are building physical AI with everything but robotics. So we're not robotics at all. We are building, because the world around us, the physical world around us, runs on sensor data. And it's not camera data. If you work with the factories, which we work a lot, if you work with logistic companies, we work with doctors, there is almost no sense of visual data. A lot of the data was objective measurement of physical world, how the physical world runs. And the people don't have very hard time understanding this data and using this data, because it's fundamentally non-perceptible. You cannot look at a radar signal and say, oh, I know this is a hand or this is an arm or something. You're just not going to see it. So what we are building is physical AI, which helps people become smarter, which can take data from physical world and the problems like energy grids control is one of our customers, or manufacturing in other customers, all this complex data, and turn that into the insight and make people smarter. And this is actually quite big problems and a big opportunity. Actually, sorry. All right. So the question would be like, okay, so, but don't we have it already? Don't we have already all this data in the world? Didn't people already use AI and ML for solving problems? Well, same robotics, right? Robotics has been around forever. I think the biggest difference with physical AI, compared with previous ML approach and AI approach, is generalizability. Because until now, and when we work at Google, and before that I was working at other companies, every time you want to build a model to understand some part of the physical world, you're building verticalized solutions. Same with robots. All these robots were special purpose, very narrowly defined. And every time you want to build new solution, it's another 2 years, another millions of dollars. So it was fundamentally very difficult to do. What's really exciting about current generations of AI techniques, and basically based on transformers and foundational models, is that we're building general purpose AI models that can understand physical world in general. And generally from sensor data directly through reinforcement learning, for example. and then generalize to tasks, use cases, condition, and applications vertical, and you don't have to train the model for every task. The model understands how the world works. So you have like one model which can do across a variety of use cases, across a variety of applications, and so forth. And that's very attractive because you have like one model to be applied across all the industries and all the opportunities which is there. So think about like ChatGPT, but for physical world, be able to like understand the physical world around it. So I think we're very excited about this opportunity because coming from our previous background, you know, we have customers now. I don't have, unfortunately, too many slides to show about, but across all these industries, like for example, we work with energy companies to understand data, the load on the electrical grids and understand where the peaks electrical grids happens when there's a potential to the blackouts. We're working with a healthcare to understand how people move in space and when they can fall, predictive healthcare directly from sensor data. We're working with a construction to find safety risks and operational inefficiencies, or manufacturing, finding defects in the equipment and manufacturing. And we're trying to build this using one model, a single model we can do this. And I think the opportunity is really big from our expectations, like what we're looking at. Non-robotic physical AIs can be really big, like space to people willing to pay if we can solve their problems. This is kind of like a very rough estimate. But what's interesting here, the real opportunity is to have one foundation model that controls 80% of the world economy, because this is all use cases combined is about 80% of the world economy. You can have one model which can apply to all of that. I think that's a real opportunity. So that's what we're trying to chase, right? We're building Newton, which is a physical AI foundation model, and also deployment platform, because you can't just like put a model on Hugging Face and expect some factory download it and use it. You have to build the entire platform to deployment, which can encode the entire physical world through sensor data directly, and then understand and solve a variety of real-world problems, just similarly as today's foundational model can solve text problems and so on and so forth. So this is a high-level diagram how the model works. We combine both contextual information, which is text data describing, you know, the specific task conditions, specific environment conditions on this construction site, and so on and so forth, with the real-time sensor data capturing the physical world. They're encoded in common representation, we call it common embedding space, and a variety of decoders allow us to extract data from those, from the common encoding, and to answer questions which people can ask. And I'll show you some examples of how the model works, and you will see them. But I think what I would like to talk a little bit about it, like if we talk about the model to understand the physical world, what does it actually mean to understand physical world? Because the way you answer these questions will define the architecture of the model. Like what's the high-level model could be which can understand physical world? And the question, what does it mean to understand physical world, is actually a complex question. We kind of, if you ask, like, what does it mean? Everybody's like, well, probably it's obvious to understand physical world. But let me give you an example. A little riddle, which I came up with to explain why it's not a simple question. So imagine this medieval Germany, I think it's Leipzig, and there is on a street, you have a student and a clockmaker living next to each other, right? And the clockmaker can make a pendulum clock, right? Because he's a master, he's making pendulum clocks. But he cannot write a differential equation of pendulum. And a student can write differential equation of pendulum because he's studying with Leibniz, you know, who invented calculus. But he cannot make a pendulum clock because he's a student. Like, which one of them understands the physical world, right? Student or the clockmaker. And I think the conversation in physical AI very much split along this line. You're either building a clockmakers which can simulate something or make a robot put in boxes or synthesize future kind of, you know, like simulation of the gas dynamics using physical AI, or you're making a student which can derive equations or explain something and write a formula or describe falling ball on the floor. But the reality is none of these two directions do not lead to full understanding of physical world. You need to have both. You need to have the approach where you have two kind of models on the same root, which can both explain the physical world, but also understand from the point of physics. So the Newton is fundamentally built as two expert models underneath the same roof, right? It's one model responsible for physical reasoning, which learns about physical world through reinforcement learning directly from sensor data. Another one is focused on semantic understanding and interpretation of the physical world, which can, very similar to current multimodal models, it can interpret the sensor data and explain what's happening there. And then data coming from a variety of sensors for the encoders, and the output from one is a physically accurate representations, which not necessarily based on human understanding. And the bottom one is interpretation of that. So it's kind of actually surprising when DeepSeek came up, R1, they kind of have a similar approach. They don't have like one gigantic model. They have this multiple expert models working together. We've been working this approach for a while. So like this is a combination of the two. So let's maybe show examples of how this two model works. And I'll do the next step and show how the intersection of them works. So the top model is basically based on reinforcement learning, where you train the model on a subset of just physical data with no human input. The model on itself builds a physical model of the world, and the question becomes, if you train the model with a subset of physical information, how well the model can generalize on physical parameters they've never seen before. And that's a recently paper we published, and you guys are welcome to go download the stuff. It's surprising how well the model can generalize across different physical sensors. This is a model. I'm going to skip it. It's an encoding and then decoding model. It's a combination of both. It's not purely decoder model, but this is the video, a little bit sped up. So what's exciting about this video is that you have a sensor accelerometer on the bottom of this weight. Like everybody see this experiment. This is classic school kind of like project you can do, like physics. Basically, it's an elastic pendulum moving up and down, right? And you have accelerometer underneath. On the left side here, do you see my cursor? Okay, so here you have the actual measurement, and here the prediction. And the model predicts the whole thing. What it does, the model doing pretty good prediction of regular motion. But at the same time, it's also very good at doing prediction of chaotic motion. So the same model predicts both chaotic motion and stable motion using the same set of weights, same equations. If you try to actually do a differential equation of how chaotic motion, you have to write complete different set. Now, what is exciting about it, about this approach, is that model does not have accelerometer data, has not been trained accelerometer data on the system. It's zero shot. The model have never seen this system is capable to predict both chaotic and motion on its own. What is more is that Newton was able to predict not just chaotic motion, this is another example of chaotic motion predictions, but also thermodynamic motions. On the right side, you have thermoelectric system, which we built, very simple one, where you have a semiconductor between two plates of electrode, and difference in temperature creates electrical flow. So the same model with the same weight is capable to predict behavior of thermoelectric behavior in this particular experiment and mechanical motion. So it's fundamentally, the models build some form of its own representation of the physical world, which is not informed by any equations or any sort of like human's input. We didn't teach it laws of physics. It figures out on its own. Now, this is very simple examples, of course, but 1 second, I need to switch the slide. But the question becomes, of course, what's the interesting thing is this also really well generalizes to very complex, not just toy examples. This is the data sets we downloaded for complex problems such as like electrical consumption, oil temperature electrical transformer, something you cannot write equation of. And the question is like, can the model predict this if it's never been trained on this data before? And it was quite exciting for us to see. The blue is, in the red and the orange is our model, Newton, be able to predict, and the smaller the better. This is the error rate for the actual thing. And what you can see here is that, and the blue one is a classic approach. We collect the data, train the model, and then run on this data and see how what model does, right? So the target-trained classic approach, where you have domain knowledge embedded in the model, performs worse than zero-shot model, which is trained on a broad variety and reinforcement learning-based data from about physical data. So with zero-shot, all this task in outperform, which is quite exciting because you can go to the factory. It's like, we don't need your data. Our model can restate your physical process straight out of the box. Now, we're actually having a couple of projects like this trying to figure it out. So this is another work which is not in the paper and published, which also model can do is, again, reinforced learning, start clustering data and be able to separate different classes of data in different pieces, right? So it does now classification, also zero shot. So again, so this is an interesting point. So like this part of the Newton brain, which is responsible for understanding physics, is have a physical model of the world, which is quite accurately can predict a variety of physical effects, not just across sensors and tasks and conditions, but entirely different kind of like areas of physics, be able to predict by that. So we're kind of still digging it, why it can do this. So this is one part of the brain. And the bottom part of the brain of Newton, kind of left side of the brain, the physical reasoning. And the right side of it is semantic interpretations. Because when we think about the physical world and try to describe it in words, the ball falling, the ideas of falling and the ball and up and down and gravity, they don't really exist. They made up. Humans made them, right? So, and most of the AGI work is focused on trying to take the data from the real world and trying to create this semantically human way understanding, human interpretation of the physical world, described in a human concept. So we have our own kind of multimodal model built. Newton has this other part of the brain, multimodal thing, which can do like this is a radar, images, text. We can add many kind of encoders, and it does a variety of interpretation tasks. So this is an example of real-time radar interpretation, how it could work, right? How does it work? This is a real example of same model understanding how things behave. So let me pause the video, I'll show you something. So, all right, so this is a radar in the middle, and the radar looks outside, and this is signal from the radar. You can see completely interpretable. And then the model interpreted in the text, basically trying to figure out like what person's doing and describe it in human understandable forms. Obviously, the radar doesn't see a person. Radio just see the target, but by giving the model context, this is a person described its motions, the model capable to map it out. So you can see this. So person's nearby, person's stationary. As a person moves around, the model constantly trying to interpret the person's receding quickly, and person is nobody's present. So this is an example of how non-visual data can be interpreted using our model. Now, we recently, like after the R1, so one of the important things is it has to be very kind of physically accurate. The model has to be able to represent spatial concept in a way which is accurate and correct, because we're working with the customers for them it's very important. And so we kind of run this comparison between Newton and Gemini and OpenAI, and we're really much focused on spatial understanding. So this is an example of task which we're doing quite well. The question is, identify person near car. This is a classic topological relationship between objects and the world, spatial relationships, where person near car is kind of high-level semantic form, and the model draws bounding boxes around the people. So we run it with Gemini and OpenAI. After DeepSeek came out and everybody started like running all this like comparison, but like, let's try to do this. And it's surprisingly that like general purpose model don't do really well on spatial relationships. Like if you ask the questions Gemini and OpenAI, OpenAI kind of draw box somewhere here. Gemini just like selects every person. They don't really have a concept of near or far. There's another example, person on the bench. There's a different types of topological relationship where where objects are connected. Here on the corner, you can see Newton seeing person on the bench. Again, Gemini again just like tracks select every person, and this is OpenAI, just random people. This is a more close example that you have a like ball on top of the book, and again, so like the model we trained has a really clear understanding of like relationship balls on the book, while Gemini kind of went to this loop, creating a bunch of stuff, and OpenAI draw the box somewhere in there. Here we go. So I think it's not about like these models, but I think again, like you focus on a high quality data, specifically focus on spatial tasks, you can build really precise models relatively quickly. That's the video. Of course, we do also video example. It's basic video description. The guy throws the ball and just kind of like describes things. That's kind of we do video. Also, presentation is just an example. This is an interesting example of what model do. This is a client we're working with on construction side. So the model been pre-trained a very large amount of semantic data and visual data about like behaviors in the physical world. The model never saw barges and never saw excavators, right? So we added labeled data of the barges and excavators, and they trained the model so to recognize it. So like we also have like structured output of the models, obviously, so we can it comes up with exact coordinates and stuff. So this multimodal output show the barges and excavators. And what was really interesting for that, and that's what we're against, why these physical AI models for the world are very important, is that they're capable to generalize previous knowledge to the new knowledge. Once we teach the model about construction, it was able to explain why the productivity was low when there was a snow. So the concept of snow and connection to productivity and the reason for that was known from pre-training side. And by adding a little bit of knowledge about excavators, we rapidly could get model to explain why construction was slow on site. So this is kind of, we see this more and more generalization capabilities when we have physical AI models for the physical world. Anyway, so this is a model kind of physical reasoning and semantic reasoning. It's got two blocks of the model connected together. I think what's most exciting is when you can map from physical reasoning to semantic reasoning, where you can connect the top box to the next box together, where your physical intuition of the model connects to semantic understanding. So this is an example here, is that here you have an accelerometer in the box, and it's been analyzed by our continuous signal tracking, and it's be able to understand basic behaviors of the box, basic components of the box. Using the, you saw the previous classifications, that piece. And then the person moves around, and then what you can do is projects to semantic space, and you can ask, can you look at this data and tell me the transit status of the package? So the package and transit status is being told to the model, and then you move around, and it's model can able to understand this package is still, package is in motion, package is, again, still again. And then you can go into the same data, you can put different questions. Guys, can you say the package is mishandling? And now the same data being interpreted completely differently because the data is being projected from the physical space into semantic space with this new information. And the model is interpreted, the package is shaken, package has been handled gently, and package dropped. This actually was coming from a real use case with people who ship a lot of vaccines, and they need to track position of the box. And of course, you can also go other way around. You can go from semantic interpretation of the world into the physical reasoning. It's a generative piece of the model which Newton can do. So we can now generate stuff from semantic interpretations. So this is an example of work we did with a automotive company, where you're asking question, pay attention to the car in front and select it. Now, this is a tricky question because all those cars in front. There's not cars which is not in front. So the model should be able to physically correct and understand which cars is in front and select it around. So when the car changes lane, for example, it correctly select the car in front of the car. Anyway, and that's what we call understanding. So this is architecture of Newton came from this experiment. The understanding is not the top or the bottom. It's understanding of physical world. It's the ability to map your intuition to semantic knowledge, and from semantic knowledge to your intuition and physical control. It's very similar to humans, as a matter of fact. We able to create semantic concepts in our brain. Like I want to move my hand to the right, and I translate the semantic concept in my brain into physical motion, which plans my motion of the hand on the right. At the same time, when I hold a microphone, this information from my hand goes to my brain, and I can interpret it semantically. So that's true understanding of physical world, and that's what we're trying to build with Newton. So thank you very much.